Pressurization is all around us, literally. Earth's atmosphere exerts a pressure force which influences everything from the weather to the boiling point of water to our ability to breathe easily. That last one is especially important in aircraft, since a fuselage needs to be pressurized to an altitude where we can breathe. We just learned about the concept of pillowing, where the parts of a fuselage unsupported by frames tend to bulge out when pressurized. However, this phenomenon is sometimes difficult to see on an aircraft, since the changes are so small compared to the size of the fuselage. We could take this knowledge and accept that it occurs without seeing it directly, but if you're like me, it's easier to understand a concept if I can do it myself. Luckily, pillowing is easy to replicate using some things you might have around the house or left over from a birthday party. But Hannah, where's your hypothesis? What are you doing here without one? You might be asking. Well, sometimes I like to do quick demonstrations, in addition to my usual experiments, just to show how something works. But since you're all curious minds, we can come up with some questions to ask as we go through the demonstration. To show the pillowing effect, we'll need two simple items, balloons and rubber bands. An inflated balloon is like a pressurized fuselage without any frames on it. With no stiff support, the balloon is free to expand in all directions. When I put two rubber bands over the balloon, you can already see that the bulging is restricted in those areas. Look even more closely. The pillowing effect is quite clear. There's an obvious indentation at the band as the air inside of the balloon redistributes to the non-restricted sections. So what do we think will happen when a third rubber band is added to the balloon in between the others? Will this create larger peaks in between the bands, since more stiffness is added? Let's find out. When the third band is added, it starts to flatten out the peak created by just the two rubber bands. Interesting. We can still see the pillowing, but it's less pronounced now. Let's add two more rubber bands. What can we see? It seems that the pillowing is still occurring, but the bumps are much less prominent, and there's more consistency between each rubber band. This is exactly what's happening in an aircraft fuselage. If we look at a schematic diagram of a fuselage, you might wonder why there are so many frames. If the point of aircraft design is to be as light as possible, why are there so many stiffening frames which are adding a lot of weight? Why can't engineers just make the fuselage skin thicker, thereby increasing stiffness? Interestingly enough, adding thickness to the skin to the point where it is stiff enough on its own would be a much heavier option than using frames to support a thinner skin. Considering the huge pressurization forces on a fuselage in flight, it would take a lot of extra material to achieve the same results. And what we see with the balloon and rubber bands is that as more stiffening elements are added which contain the pressurization forces, less pillowing occurs, and the distribution of forces becomes more equal. We can contain the pillowing effect while keeping a thin fuselage skin, thus minimizing weight. Now that we've taken a quick break from our usual hypothesizing, it's time for me to get back to working out our next experiments. See you next time!